Anthony Spradling, and this is my Lab 2 video on projectile motion. In this lab, the purpose is to observe the motion of a paper ball that is thrown in the air like a projectile. We want to compare the position data that we will use a tracker to find with experimental models we construct in GlowScript. We're going to use models to compare the position versus time graphs, trajectory graphs, tracker models, and GlowScript computations. Some of the physical principles used in this lab are position, velocity, drag, position update formula, velocity update formula, and Newton's second law. In the end, we found some slight deviation in the computational model compared to the tracker data, and when we added drag, we saw even more deviation. In the lab, a few basic formulas were used to determine position and velocity. These equations allow us to use Newton's second law to get an estimation of where the object will be based on the net forces being applied to it. So these are some of the main physics ideas in the experiment. In order to create the computational model, we needed to set initial conditions. We found the initial velocity using the v-average formula and picked the first 2 points in the data. We found the v-average between these two. The initial position vector was given to us by tracker. In the computational model, we needed to create equations for net force, and we used the fundamental physics principles we know to create the equations on the right. We assumed that the only forces acting on the objects were gravity and drag, so we had to create two computational models to display what happened in each situation. This is the tracker video we used. As you can see, the paper ball is displayed on the white, and in its motion and trajectory is highlighted in the red point masses across the screen. The ball started at a height above the 0 in the y direction and moved to the left in the negative x direction, ending at 0.00. In this experiment, we define the ball as a system and the surroundings as everything else in the environment. This includes the air and particles that affect the ball's motion. This is a GlowScript model with no drag. The initial conditions are highlighted with arrows along with other important information. Again, we found the initial velocity using the v-average formula on the previous slide. We broke the computation up into time steps of 0.033 seconds and had it run until time was 0.233. At each iterative step, the model exercised the equation highlighted with an arrow that found the new velocity and position for the object using the F-net equation highlighted. In the experiment with no drag, the only force acting on the object was gravity in the negative y direction. This is a GlowScript computation for the model that includes drag. This one is a bit more complicated because we had to include and define other forces that would iterate with the model. These equations are marked with an arrow. We still use the same initial conditions from the first computation model because they represent the same motion. Here we have a visual representation of the data we collected that compares all the models. We can see that the computational model with and without drag seem to be slightly off the mark, but this is logical. If the model that does not include drag has a y position lower than the tracker position, if we add another force that thwarts its motion, it should make the ball's position even lower. Here we're going to discuss some possible sources of error in the experiment. Some of these include camera distortions, differences in wind resistance and friction along the surface of the ball, the regular shape of the ball, and the air conditioning and other air movements in the room. Because of the shape of the ball, as it moves, it's going to hit air particles that slow it down. Because of its awkward shape, some of these forces are going to be applied at different angles, causing different normal forces in different directions. This is what causes the ball to spin. This spin takes some of the kinetic energy of the ball and converts it to rotational energy. Since that energy is going to make the ball spin, it has less energy to move linearly. If we examine the velocity versus time graphs predicted by our models with and without drag, we can see that none of our models predict a terminal velocity. A similar experiment we could do would be to drop the ball from a higher height and record more data. This would allow the ball to reach a terminal velocity we can measure. If the ball were thrown up with the same initial speed as in the experiment, the time it took to reach the ground would be longer. This is because the velocity is now only in one direction instead of two. If we look at it in component form, we know that the angle velocity will be much less in both directions since it has to be split between the two using trig. This would mean that the ball will go higher in a vertical distance and essentially would take longer to reach the ground. Thank you.